This video covers section 1.1, which is an introduction to chance models. And we're going to look at the Can Dolphins Communicate example, which is on pages 23 to 28 of your textbook if you want to look at more details. Earlier when we looked at the organ donor example, we saw that depending on which default was used, opt-in, opt-out, or neutral, there were different rates of people agreeing to be organ donors. And we ask ourselves, are these differences statistically significant, or is it plausible that they occurred by chance alone? So when we say that a result is statistically significant, all that means is that the result is unlikely to occur by chance alone. And it's important to note here what statistical significance does not mean. It does not mean that the effect is large, and it also doesn't mean that the effect is important. So we have to be sort of careful with this term in that it's really limited. All it means is unlikely to occur by chance alone. So in the preliminaries, we said that the results were statistically significant, but we didn't get into the math behind it. So that's what we're going to start doing in this chapter. So this example is about whether or not dolphins can communicate abstract ideas. So we have these two dolphins named Doris and Buzz. And they've been trained in this very specific way. So they've been trained that if the headlight in their tank is shining steadily, that means that they need to push the button on the right. And if the headlight is blinking, that means that they need to push the button on the left. So for a while, they're trained like this. So if it's blinking, they're going to push the button on the left. And then eventually, the trainer sort of changed the game. And in order to get their treats, Buzz had to do his first, and then Doris had to hit hers. So now they have to coordinate a little bit. And then in the last stage, they actually took Buzz's headlight away. So remember, he still has to hit his first before Doris can get her treat, but he can't actually see the light anymore. So they've put this partition between them in the tank. Buzz doesn't have his headlight, but he still needs to hit either the left or the right, depending on what Doris's headlight is doing. So they did see that she would go over to the partition and make sounds at Buzz. So probably not exactly like that, but that she would make some sort of sound, and then he would hit the button that he was supposed to. So that's our setup. In order to be rewarded, Doris must communicate with Buzz about which button to push in their tank. So the observational units here are not the dolphins. There's only two dolphins, and we're not going to record information about the dolphins themselves. The observational units are Buzz's attempts. And then for each attempt, we're going to record whether he got it correct or incorrect. So that's a categorical variable. So sometimes if you're having a hard time figuring out what the observational units are, it can be helpful to think about the variable first. Correct or incorrect, okay, that's not actually something that describes Buzz, that's something that describes his attempts. Okay, so that was the second step, that was the design step. In step 3, we're going to explore the data. So we're going to look at a particular phase of the study where the researcher had Buzz attempt to push the correct button a total of 16 times. And in this sample of 16 attempts, Buzz pushed the correct button 15 out of 16 times. So our sample size is 16. A lot of times we use an N to represent that. And then we're going to calculate some kind of statistic. A statistic is just a numerical summary of the sample. So there's a couple different things that we could use here. We could just use the number correct. So we could just use 15 as our statistic. Or we could use the proportion correct. So these are just two different numerical summaries that we could use to describe our sample. And when we talk about a proportion, we're going to label that as p hat. So p hat, this is our sample proportion, 15 out of 16. So we know that Buzz got it right 15 out of 16 times in this sample, but that's not really what we're interested in. We want to know the long run proportion of times that he would get it right. We call that the probability. So we want to know the probability of him getting it right based on Doris's whistle. So this unknown long run proportion is called the parameter. So our statistic is what happens in the sample. The parameter is what happens in the long run. So this statistic looks pretty impressive, right? 15 out of 16 correct. So there's basically two different explanations for that. One is that dolphins really can communicate, right? That's the sort of exciting explanation, is that there is some kind of communication going on. But something we're going to get in the habit of in this class is that we always have to consider sort of the boring explanation. We're going to call it the just by chance explanation. It's possible that Buzz was just guessing all 16 times. He really had no idea what she was saying, and that he just got lucky in this particular sample and got 15 out of 16 right. So before we can rule out that just by chance explanation, we have to know how likely would it be to get 15 out of 16 if that's what was going on, if he was really just guessing. So we're going to do a simulation, and in the simulation we're going to assume that he's just guessing. So not that he's communicating, we're assuming that he's just guessing. So there's only 2 buttons in the tank, so whether or not he gets it correct is basically a 50-50 chance, just like a coin flip. So we're going to flip a coin, and each flip is going to represent one of Buzz's attempts. And we'll just let heads equal correct and tails equal incorrect. It doesn't really matter. And there were 16 attempts in the sample, so we're going to flip the coin 16 times. So basically we're trying to see what would a sample of 16 look like if somebody was really just guessing. For each set, we're going to record a statistic to summarize the sample. And here I'm just going to use number correct. It doesn't actually matter which one you use, but I think that's the simplest. And then we're going to repeat this many times. So this is our first time using applets in this class, but we're going to use these over and over again. So I would just Google ISI data and applets, and this should take you to it, ISI applets and data. Oops, I did it backwards. And click on that, and then I would go ahead and bookmark that because we're going to use this over and over and over again. And we're going to look at the one-for-one proportion. So the way this applet works, if I click draw samples, it's flipping coins 5 times. That one's weird. It actually came out all heads that time. And it's recording the number of heads. So 5 showed up down here because we got 5 out of 5 heads. If we do it again, this time it came out 4 heads, so we have another dot down here at 4. But I don't want 5, I want 16 because that was my original sample size. And I'm going to turn off the animation just because it goes kind of slow. So we can see out of these 16, 10 came out heads, so that's like 10 correct, 6 incorrect. Not quite as good as Buzz did. If we do another sample, that one's also 10. This one came out 7 and 9, so got it right less than half the time. And we're basically just seeing, okay, how could this have played out, right? This set of 16 guesses, how many do we think that Buzz would actually get right? So we're starting to get a sense of the range, right? The different numbers that Buzz might get correct. So I've got 25 so far, and you can see the highest that's showing there is 13. Right? We're not getting any like Buzz got with the 15 out of 16 correct, but 25 isn't really enough to make a judgment. So I'm going to do a really big number here. Let's see, let's try to get up to 1,000. Let's do 975. Okay, so now I have a really good idea of what values are possible when Buzz is really just guessing. And I can count and see how often did I get values of 15 or larger. And you can see actually here out of these 1,000, it didn't happen at all. Let's go ahead and keep going. Let's do 9,000 more to make 10,000. Okay, so out of 10,000, only 2 of them were 15 or higher. So if you think about Buzz being lucky, he was really, really lucky, right? It would have to be something that only happens 2 out of every 10,000 times. So going back to our notes here, remember this picture is showing what would we expect to happen if Buzz were really just guessing. And we counted all of the ones that were 15 or higher, right? Because this is Buzz here at 15. And we saw how many times we got outcomes like that. So this is unlikely, right? Getting 15 or more correct only happened in 2 out of 10,000 samples. So 2 out of 10,000, that would be extremely lucky. So thinking back to that just by chance explanation, is that actually a good explanation for our data, right? Is that compatible with our data? Well, not really, because the just by chance, the just guessing explanation would practically never lead to data like ours, right? So I would say this is really not a plausible explanation because it's just so unlikely that you would get 15 out of 16 correct this way. So this is how we talk about our strength of evidence, right? Once we've ruled out that he was just guessing, now we have strong evidence for the other explanation, right? So we have strong evidence that Buzz wasn't just guessing, that there was something else going on here. So there's still a few more steps in our statistical process. Formulating the conclusions, if Buzz wasn't just guessing, does that prove that Buzz and Doris can communicate? And if so, what does this say about other dolphins, right? Can you actually generalize this to all dolphins? Or is it possible that there was something special about these, right? Probably some more research would be necessary before you could extend this too far. And looking back and ahead, we're going to revisit the original research question and think about the limitations of this study. And we'll actually do some of this in a group discussion later on. So this logic of inference isn't easy, so I'm going to give you a minute to process this and put it in your own words.